शायर हूँ, पल तो पल मेरी कहानी।
Wait for 2 minutes here.
Hello.
Hello. Are you able to hear my voice?
సార్ ఫస్ట్ నుంచి చెప్పండి,
మళ్ళీ
మళ్ళీ ఫస్ట్ నుంచి చెప్పండి.
సరే. Hello? Is it audible? Audible? Are you able to hear my voice? Okay. Again, we go back and we start from beginning on. Now today we are going to start the one of the subtopic of mathematics, that is linear algebra. The weightage of this topic is 1 to 3 marks. In the year 2020, one question was given from linear algebra topic, and that is a 2 marks question only. So only 2 marks were given in the year recent examination. In the last year 2019, one question was given from this linear algebra, and that is 2 marks problem. So totally 2 marks were given from this topic on. In the year 2018, 2 questions were given from linear algebra. Out of 2 questions, one question is 1 mark question, one question is 2 marks. Totally 3 marks were given from this topic only. So you may get more than 1 mark, or we may get more than 2 marks or more than 3 marks. That is, you may get only 1 mark or 2 marks or 3 marks or more than 3 also, like this only. If we get more marks in this subtopic, you will get less number of marks in other topics. Or if you get less number of marks in this subtopic, you will get more marks in other subtopics. Okay. Now these are the subtopics. Determinants. In the linear algebra, again, we have 5 subtopics. Very first one is determinants. Second one is inverse. Third one is rank. Linearly independent, dependent vectors. Fourth one, solution of system of linear equations. And the last one is eigenvalues, eigenvectors, and Cayley-Hamilton theorem only. So these are the 5 subtopics of linear algebra. We start the determinants only. From the determinants topic, we have a gate questions on 2 by 2 determinant, 3 by 3 determinant, and 4 by 4 determinant. 2 by 2, 3 by 3, 4 by 4. Most of the gate questions on 3 by 3, 4 by 4 determinant on. That is why we start with the second order determinant and we stop with the fourth order. That is, in this determinant subtopic, we discuss about the methods of finding the determinant of second order, third order, fourth order. And whatever we discuss the method for fourth order, we use the same method for next higher order. So whatever we have the method for fourth order, and we apply the same method for next higher order only. That is why we start with the second and we stop with the fourth order only. So this determinant topic is useful for other 4 subtopics indirectly also. Determinant is required for inverse, rank, solution of system of linear equations, and eigenvalues, eigenvectors only. In the year 2019, one question was given, that is a 2 marks question, on eigenvalues, eigenvectors. But indirectly, that is a question from determinants only. Without determinants, we cannot do that. We cannot do that question only. So let us start with the determinants subtopic. In this determinant topic, before going to write the 2 by 2 determinant, third order determinant, fourth order determinant, we start with the general matrix only. This is the general matrix with the general elements and general order. We write the same matrix in short form like this. In short form like this. So these 2 are short forms of this general matrix only. So instead of writing the elements, always we write the matrix with a general element like this and general order. Let us go to the next page. Second order determinant. First of all, determinant is just number. Matrix means arrangement of numbers in the form of horizontal lines and vertical lines only. Let us start with the second order determinant. If A is 2 by 2 matrix with the elements A11, A12, A21, A22, then the expression, here we are writing the expression. The expression is within the 2 single vertical bars, two vertical bars. Within the two vertical bars, we write all the elements of 2 by 2 matrix. Then we get an expression. This expression is called second order determinant of second order matrix only. And it is denoted by like this. Within the two single vertical bars, we write matrix A only. It is a notation for determinant of A only. We read this as determinant of A. Should not read this as mod A. This is only determinant of A only. Modulus is defined for numbers. Determinant is defined for matrices only. So in matrix theory, we never consider modulus of matrix only. That is why don't pronounce this as mod A. It is only determinant of A only. So we denote the determinant of A as like this or like this, data of A only. Here the unique number, that is the product of diagonal elements A11, A22 minus A12, A21 is called the value or expansion of second order determinant of 2 by 2 matrix only. Therefore, determinant of A equal to A11, A22 minus A12, A21 only. This is about the second order determinant. We require this second order determinant for other order determinant, further order determinants only. For third order, we require second order. For fourth order, we require third order and second order. For fifth order, we require the fourth order, third order, second order, like this only. We require the lower order determinants for higher order determinants to write their values. Okay, let us go to the third order determinant. Like this second order determinant, we won't write in written form, just we write the expression for third order, fourth order, and so on, and then we write its value only. Okay. Now to write the third order determinant value, there are three methods. To write the third order determinant value, there are three methods on. This is, first we start with the method 1. In method 1, we write the expression like this. Here I wrote all the 3 by 3 matrix elements within the two single vertical bars like this. Here I wrote all the elements of 3 by 3 matrix within the two single vertical bars. That is like this: A11, A12, A13, A21, A22, A23, A31, A32, A33 only. If you write all the elements of some 3 by 3 matrix within the two single vertical bars, then this expression is called a third order determinant of third order matrix only. According to method 1, first we choose any one row or any column, and then we expand along that row or column only. In general, we choose the first row. Now here we have chosen the first row. After choosing the first row, we should write the place sign of each element. We should write the place sign of each element just above the element, or position sign of each element just above the element. In general, for general element Aij, the place sign or the position sign is given by -1 whole power I plus j only. This is a formula to write the place sign or position sign of element only. Now we are expanding along the first row. That is why for only first row elements, we write the place sign. For very first element, the place sign is given by -1 whole power 1 plus 1. The power is 1 plus 1 is 2. The 2 is even number. Because the even number, this sign becomes positive. So above the A11, we write the positive sign like this. Next, for A12 element, sum of the two suffixes is 3. 3 is odd number. Its sign is minus. So minus. A13, its sign is positive 1. In the first method, we choose row and then we write the sign of each element just above the element like this only. After writing this sign, we expand along this row. To expand along this row, we choose the first element A11 along with the sign plus A11. After choosing this element, delete the corresponding row, corresponding column. After deleting the corresponding row, corresponding column in 3 by 3 matrix, we can obtain the 2 by 2 matrix. For this 2 by 2, we take the determinant A22, A23, A32, A33. And then we go to next element A12, its sign is minus A12. After choosing this element, delete the corresponding row, corresponding column, and then write the determinant of this 2 by 2 matrix. That is this. And then we go to the last element A13, sign is plus A13 into, delete the last row, last column, write the determinant of 2 by 2 matrix. This is the determinant. So for third order, we require the second order determinants. So expansion of 1/3 order determinant, expansion of 1/3 order determinant is same as expansion of 3 second order determinants. Expansion of 1/3 order is same as expansion of 3 second order determinants. This is method 1. This is method 1. This method 1 is called expansion method or Laplace expansion method. Next, we are going to method 2 only. Already I told you that there are 3 methods to write the value of the third order. So out of 3 methods, method 1 is completed. This is method 1. Next, method 2. Method 2. In method 2, again we write the expression for some 3 by 3 matrix like this. This expression is called third order determinant of some third order matrix only. In second method, to write the value of the determinant, we have 2 steps. In first step, rearrange elements along the first row and along the last row. Along the first and last row, we rearrange elements. Next, in the second step, we choose the 6 lines. By choosing the 6 lines, we write the value of the determinant. So within 2 steps, we write the value of the determinant for this third order. Okay, let us come to this determinant. We rearrange elements along the first row. Here the rearrangement is write the last element before the first element outside the determinant. Like this. Write the last element before the first element outside the determinant. Again, write the first element after the last element outside the determinant. Like this. This is the rearrangement of elements, just like this. Only corner elements. Rearrange the corner elements. Write A13 before A11 outside the determinant. Write A11 after the last element outside the determinant. Do the same thing along the last row. Along the last row, write A33 before A31 outside the determinant. Write A31 after A33 outside the determinant. It is like this. This is the first step, rearrangement of elements along the first and last row only. Step number 1 is completed. Next, we go to second step. In second step, we consider 6 lines. Okay. Out of 6 lines, we choose the 3 lines from top to bottom, 3 more from bottom to top like this. For this, we draw like this only. Let us start with A13 and draw the line like this, top to bottom. Say this 1. Next, go to next element, draw the line parallel to this. Parallel to this. Say this 2. Go to next element, draw the line parallel to this. Say this 3. These are the 3 lines from top to bottom. After this, we draw 3 more lines from bottom to top. Start from A33. Draw the line like this. Say this 4. Go to next element, draw the line parallel to this. So this 5. Next, go to next element, draw the line parallel to this. Like this. So like this, we draw the lines, 6 lines only. 3 from top to bottom, 3 more from bottom to top only. Up to here, drawing the lines is completed. Using these lines, we write the value of the determinant only. Therefore, determinant of A equal to sum of the 3 lines from top to bottom minus sum of 3 more lines from bottom to top. 4 plus 5 plus 6. This is the second method only. So first, write the expression, rearrange elements along the first and last row, and then choose the lines, 6 lines. Out of 6 lines, 3 from top to bottom, 3 more from bottom to top. Using these 6 lines, write the value of the determinant. So therefore, determinant of A equal to sum of the 3 lines from top to bottom minus sum of 3 more from bottom to top. Now here, along each line, we consider product of 3 elements only. Along the first line, product of 3 elements is A13, A21, A32 only, like this. Along the first line, find the product of 3 numbers, right here, number 1. Along the second line, find the product of 3 elements, write the number in place of 2 position. Along the third line, find the product of 3 numbers, write the number here on, like this. Later we do the problem on this also. This is method 2 only. This is method 2. Method 1 is completed, method 2 is completed, next method 3. But method 3 is, we won't write method 3 on this paper. We won't write method 3 on this paper. Just keep the method 3 in your mind only. Keep the third method in mind only. The third method is calculator method. Using calculator also, we can write the value of the third order determinant. Using calculator also, we can write the value of the third order determinant. But physically, the calculator is not allowed to the examination. That is why don't go for third method. Use either method 1 or method 2, anyone, for writing the value of the third order determinant. This is about third order determinant. Next, we go to the fourth order determinant. Fourth order determinant. Now in this fourth order determinant, first we write the expression. First of all, from fourth order onwards, only one method is there, no other method only. Fourth order, fifth order, sixth order, any order, only one method. That method is similar to first method of third order. From fourth order onwards, we have only one method, that is same as the first method of third order. That is expansion method. It is the expansion method is a general method for any order determinant, no other method for from the fourth order onwards only. Now first we write the expression. Within the 2 single vertical bars, we write all the elements of some 4x4 matrix only. A11, A12, A13, A14, A21, A22, A23, A24, 31, 32, 33, 34, 41, 42, 43, 44. Here I wrote all the elements of some 4x4 matrix within the 2 single vertical bars. So this is the expression. This expression is called fourth order determinant of some fourth order matrix only. Next we write its value. To write its value, only one method, just like first method of third order, just like this first method of third order. That is expansion method only. According to this expansion method, what do? Just we choose one row or one column and we expand along that row or column after writing the place sign. Now we follow the same method here also. Now to expand the determinant along any row or column, We can choose any row, any column. But here, in general, we choose the first row. So here also we choose the first row. After choosing the first row, we should write the place sign of each element. Without checking the sum of the suffixes is even or odd. Already I told that how to write the place sign for any row or column in any order matrix. Now here we write the place sign. For any order determinant, A11 element, the sign is always plus only. So we start with a positive sign for first element. After starting the positive sign for first element, alternately write the minus plus only. And we are expanding along the first row. Only for the first row, we write the place sign of each element just above the element. After A11, A12, for A12, next minus, next plus, next minus, like this. Start with the positive sign for first element and then alternately write the minus plus like this. So writing the sign is also completed. Now we expand along this first row. This is equal to, take the very first element A11, its sign with its sign. So plus A11. After choosing the plus A11, delete the corresponding row, corresponding column. For A11, corresponding row is first, corresponding column is first only. That is, for this element, the corresponding row is first row, corresponding column is first column. After deleting corresponding row, corresponding column in this fourth order, we'll get 3 by 3 matrix. For this 3 by 3, we take the determinant. A22, A23, A24, 32, 33, 34, A42, 43, 44. Next, we go to second element. First element is completed. After this, we go to second element. Second element is A12, its sign is minus. So minus A12. After choosing this element, delete the corresponding first row and corresponding second column. First row, second column. Then write the 3 by 3 determinant. A21, A23, A24, A31, A33, A34, 41, 43, 44. Plus, next element is A13, sign is plus A13 plus A13. After choosing the A13 element, delete the corresponding first row, delete the corresponding first row and corresponding third column, and then write the determinant of 3 by 3 matrix. A21, 22, 24, 31, 32, 34, 41, 42, 44. Next, last element is A14. Its sign is plus. Sorry, sign is minus 1. Minus A14 into determinant of 3 by 3 only. This remains after deleting corresponding first row and corresponding third column. Then this is a 3 by 3 matrix. For this 3 by 3, we write the determinant here. 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, 4, 1, 4, 2, 4, 3. It is the method for writing the fourth order determinant value. So expansion of 1/4 order is same as expansion of 4 third order determinants. Expansion of 4 third order determinants, because along any row or along any column we can find 4 elements. For each element into 1, it's lower order determinant only. If it is a fourth order, its immediate lower order is third order only. So expansion of 1/4 order is same as 4 third order determinants. Expansion of 1 third order is 3 second order determinants only. Expansion of 4th order is 4 third order. Similarly, expansion of 1/5 order, expansion of 1/5 order determinant is same as 5 4th order determinants. In general, expansion of nth order determinant is n minus 1 order determinants only. n minus 1th order determinants only. For any order determinant, that number of times its immediate lower order determinants only. is about fourth order dimension. The same method for any higher order dimension. But we have the gate questions on second order, third order, and fourth order only. Next, fifth one. After discussion of elementary operations, next we do the problems on this. Next, fifth one is elementary operations. Elementary operations, oblique transformations. Okay. Now there are three rules which are known as elementary operation. There are three rules which are known as elementary operations. These rules may be used for rows or columns. We can use these three rules for rows or columns. If we use the three rules for rows, then they are called row operations. If we use the three rules for columns, then they are called column operations. So we have two types of operations, row operations and column operations. Here we write the three rules. We won't write the three rules in written form. We write that all the three rules in symbolic form using general rows. Let us consider general rows as R suffix I or suffix J. Ith row, jth row. Using these two general rows, we write the three elementary operations in symbolic form without writing the written form only. The first elementary operation is interchange of any rows. Interchange of any two rows. That is, we can interchange any two rows in a determinant or in a matrix. The interchange of two rows is the first rule only. If you want to interchange ith row and jth row, that is written as like this. Or I two-sided arrow or J. This is the interchange of two rows, ith row to ith row. If you want to interchange any two rows, we write like this. Next, second rule is, let us consider some non-zero constant. Let us consider some non-zero constant K, and then multiply every element of some row. Multiply every element of some row by constant. That is, multiplication of a row by constant is one operation or one rule only. Let us consider ith row. Multiply every element of this row with a constant K. So this is the elementary operation, right? Or we write this as or I arrow K or I. If we write like this, this indicates position of row. This indicates operation only. In Ri arrow K or I, Ri indicates the position of row, and this indicates the operation only. We do this operation along this row position only. These are the two operations. Next, last operation. The last operation or last rule is similar to second rule only. First, we choose some non-zero constant, and then we multiply this non-zero scalar with every element of some row. First, multiply every element of some row with a constant K, and then add that row to some other row with the corresponding elements only. Multiplication of a row by constant, adding to some other row with the corresponding elements. Let us consider ith row. Multiply every element of this with the constant K, and then add this row to some other row or J. This is the operation. Multiplication of row by scalar adding to some other row with the corresponding elements. It is the operation. Or we write like this. Rj arrow Rj plus Kri. Only Rj is position of row. Rj plus Kri is operation. We do this operation along this Rj position only. These are three elementary operations or transformations only. Generally, we apply these operations on both matrices and determinants. We apply these operations on both matrices and determinants to find the rank, or inverse of the matrix. We apply these operations on matrix. To find the rank of the matrix, inverse of the matrix, we apply these operations on matrix only. Similarly, we apply these operations on determinant also to write the higher order determinant values. To write the higher order determinant values in easy way, we apply these operations on determinant. That is, these are the operations applicable to both matrices and determinants. Now, regarding last operation, we write some note point. Regarding last operation, Rj position, Rj plus Kri, we write some note point. Note point number 1. The last operation is Rj position Rj plus K or I. We can apply this operation on matrix and determinant only. So if you want to apply this operation, on matrix, we can apply this operation on matrix in two ways. Rj position arrow Rj plus K or I. Rj position or L or J plus K or I. On determinant, if you want to apply this operation, strictly we follow the same rule only. That is Rj position Rj plus Kri. So for matrix, we can apply this operation or we can apply this operation. And for determinant, we should apply only this operation only. That is, we cannot change this only. If you want to apply the last operation on matrix, we can apply this operation like this or like this only. Then the difference between these two is this multiplier L only. Like ith row with K, we can multiply Rj also with multiplier L only. If we apply this operation on matrix, the rank doesn't change, the inverse doesn't change only. The multiplier L doesn't change the rank of the matrix, doesn't change the inverse of the matrix only. If you apply this operation on matrix, we can reduce some number of steps, some number of operations only. Or instead of this, if you want to apply this operation, in some cases we require more number of steps, more number of operations only. That is why we apply this operation. But if you apply this operation on determinant, the value of the determinant will change only. If you apply this operation on determinant, the value of the determinant changes only. That is why don't apply this operation on determinant only. We should apply only this on determinant. That is, whatever we have the rule here, we follow the same rule only. And remember this here. Rj position Rj plus Kri. Ri into K. Rj into 1. Here the quotient of Rj should be 1. Whatever the quotient of Ri, doesn't matter only. But here Rj into 1 only. So whenever you want to apply operation on determinant, we strictly follow this rule only. It's a condition. On this node point, there are two gate questions. On this node point, there are two gate questions for a CSC branch only. Next. Now we do the problems on this. I'm writing the first problem. The value of the determinant of a matrix A equal to 3 by 3 matrix 2 0 1 4 minus 3 3 0 2 4 is the value of the determinant of a matrix A is. So we are given 3 by 3 matrix and we are asked to find its determinant value only. Already we know that there are three methods to write the value of the third order determinant, but we never apply the third method. We try to use either first or second, but here we do this problem by second method. Now according to second method, first we write the expression. Two, 0, 1, 4 minus 3, 3, 0, 2, 4. Here I wrote the expression for this given 3 by 3 matrix. This expression is third order determinant. According to second method of third order determinant, if you want to write the value, in two steps we write it. In the first step, you have to rearrange elements along the first row and last row only. Along the first row, write the last element 1 before first element outside the determinant like this. Write the first element along the first row after the last element outside the determinant, that is 2. That is like this. It is a rearrangement. We do the same thing along the last row. Write 4 before 0 outside the determinant. Write 0 after 4 outside the determinant. Like this rearrangement of elements on. After rearranging the elements, we consider 6 lines. Out of 6 lines, 3 from top to bottom, 3 more from bottom to top. Start with the 1, draw the line like this. Say this 1. Go to next element, draw the line, say this 2. Go to next element, draw the line, say this 3. These are the 3 lines from top to bottom. Next, 3 more lines from bottom to top. Now start with the 4, draw the line like this. Say this 4, parallel to this 5, parallel to this 6. 6 lines are committed only. Now we write the value. Determinant of equal to sum of the 3 lines from top to bottom minus sum of 3 more from bottom to top. 4 plus 5 plus 6. This is equal to, along the first line, find the product of 3 elements. Find the product of 3 elements along the first line. Write that number in place of 1 position. 1 into 4 into 2, 8. Next, along the second line, product of 3 elements is 3, 2, 6, 6, 4, that to minus 24. Next, along the third line, 0, 3, 0. At least one of the element is 0 along the line. That line product is 0. Minus bottom to top. Along the fourth line, one of the element is 0. Directly product is 0. Along the fifth line also, one of the element is 0. Product of 3 elements is 0. Along the last line, product of the 3 elements, 2 into 3 into 2, 2 into 3 into 2, 4, 3, 12. Equal to minus 16 here minus 12. Right? Equal to. What is the value? Minus 28. And check your answer, correct or not. Are you getting minus 28? Yes. Okay, minus 28 is the answer. So once again repeat. Just write the expression like this: 201 4 minus 33 0 2 4, and along the first row write this element here 1, write the 2 here, and do the same thing along the last row. Write the 4 here, write the 0 here. After that, take the 3 lines from top to bottom and 3 more lines from bottom to top. Along each line, find the product of 3 elements, write the numbers, and add all this. It is a method 2 only. Or you can follow method 1. No need to apply this method 2 only. If you feel difficulty, go to the method 1. If you feel easy, then no problem. This is first problem. Next, we go to the problem number 2. The value of the determinant of the matrix A equal to. It is a 4th order matrix with elements 1 4 1 0 0 2 0 1 0 1 0 0. Two 0 minus 1 2 is the value of the determinant of the matrix A is. The first problem is 3rd order matrix. The second problem is 4th order matrix only. From 4th order onwards, we don't have any other method. We have only one method, expansion method, general method only. According to our general method or expansion method, we choose one row or one column. We expand along that row or column after writing the place sign on. So expansion of 1/4 order determinant is same as 4 3rd order determinants only. Expansion of 1/4 order determinant is same as 4 3rd order determinants only. Now we write the expression first. One 4 1 0 0 2 0 1 0 1 0 0 2 0 minus 1 2 1. It is a 4th order determinant. According to our method, expansion of 1/4 order is 4th order. That is, we choose the one row, we write the place sign, and then we expand along that row only. Whenever higher order determinant is given like this, 4th order, 5th order, 6th order, don't go for expansion. That is, don't expand directly only by using our method only. Now, before going to expand, just look at the determinant and observe the elements. Observe the elements only. Some elements are zeros or not, check it only. In the given matrix, some elements are zeros, then consider the row or column with more number of zeros. Some elements are zeros in the given matrix, then try to choose the row or column with more number of zeros. That is, if any row or column contains more number of zeros, choose that row or column and expand along that row or column, so that we can avoid some third order determinants. Generally, fourth order determinant means four third order determinants. Some elements are zeros, we can avoid some third order determinants. Then directly we can add the value only, just like third order only. Okay, let us come to this determinant. Along the first row, how many zeros are there? Only 1 0. Along the second row, how many zeros are there? 2. Along the third row, how many zeros are there? 3. Along the last row, how many zeros are there? 1. Along the 1, along the second row 2, along the third row 3, along the last row 1 zeros. So more number of zeros are there along the third row. There are 3 zeros along the third row. Next, in the same way, along the column also, we find the number of zeros. Along the first column, 2 zeros. Along the second column, 1 0. Along the third column, 2 zeros. Along the last column also 2 zeros. So row wise maximum number of zeros is 3. That is along the third row. But column wise maximum number of zeros is 2. Compared to columns, along the third row, we have more number of zeros. That is why choose the third row only, because it is having more number of zeros compared to all other rows and columns. Like this, identify the row or column with more number of zeros. After identifying the rows and row and column, that is, after identifying the row with more number of zeros or column with more number of zeros like this, then we write the place sign of each element of that row or column only. But here we have identified that third row with more number of zeros only. Now we write the place sign of this row for each element just above the element. To write the place sign, what do? We start with a positive sign for first element, and then alternately we write the minus place, either if move right side or down side. Now we are moving down like this. First element sign is plus, next minus, next plus, next minus, next plus, next minus. That's all. Plus, minus, plus, minus, plus, minus. Choosing the row is committed, writing the sign is committed. Now we expand along this row. Along this row, the first element is 0, plus 0 into third order determinant. Next, 1 with a sign, minus 1 into third order determinant. Plus 0 into third order determinant. Plus here minus 0 into third order determinant. This 0 into third order determinant. Again 1 into third order determinant. 0 into third order determinant. 0 into third order determinant. But here 0 into something 0. This is 0 only. 0 into something 0. 0 into something 0 only. That is why don't consider the zeros. Just consider non-zero element and write the determinant only. Because of 3 zeros along this third row, expansion of 1/4 order is just expansion of 1 third order only. Now we try to write this third order determinant only. We are considering the third order determinant corresponding to this element. That is why delete the corresponding row, corresponding column, write the elements of this 3/3 determinant only. So the elements are here 1, 1, 0, 0, 0, 1, 2, minus 1, 2 only. Expansion of 1/4 order is same as 1 third order only, like previous problem. Even though it is 4th order, we require just 1 third order because along the third row we have 3 zeros only. This is equal to minus 1 into determinant of this 3/3. For this determinant of 3/3, we can use method 1 or method 2. Any one we can use only. Now I am using the method 2. 0, 1, 2, 2 only. 0, 0, minus down to top 0 plus 0 minus 1 equal to 2 plus 1, 3 minus 3. It is the answer. So like this, whenever higher order determinant is given, directly don't expand. Just observe the elements and check the elements. Some elements are zeros or not. Zeros are present in the determinant. Try to identify the row or column with more number of zeros and expand along that row or column. It is a method. Fourth order determinant. In the fourth order determinant, if we have 3 zeros along the row or column, then expansion of fourth order is just 1/3 order only. That is why whenever you get higher order determinant like this, most of the elements will be given as zeros only. Don't worry about higher order determinants. Simple elements will be given, or most of the elements will be given as zeros. Its value is -3 only. Next, we write one more fourth order matrix determinant. Problem number 3. The value of the determinant of the matrix write the matrix as fourth order matrix. Zero, 1, 2, 3. 1, 0, 3, 0. 2, 3, 0, 1. 3, 0, 1, 2, 1 is. Like previous problem, it is also fourth order matrix only, and we are asked to find the value of the determinant of this matrix only. Already I told you that whenever higher order matrix is given, to write its value, that is to write its determinant value, identify the row or column with more number of zeros and then expand along that row or column. Now I'm writing the expression. It is expression. Now if you observe the elements, we can find some zeros only. Because of zeros in the determinant, we try to choose the row or column with more number of zeros. Along the first row, 1 0. Only 1 0. Along the second row, 2 zeros. Along the third row, 1 0. Along the last row, 1 0. Row wise, maximum number of zeros is 2. That is along the second row. Next, column wise, 1, 2, 1, 1. Compared to, that is all other columns, along this row, along this column, we have more number of zeros only. Row wise maximum number of zeros is 2, column wise also maximum number of zeros is 2 only. So along the second row or along the second column, we can expand on, because the second row, second column is both are containing the same number of zeros only. So we can expand along the second row or second column. Let us expand along the second row only. Now before going to expand along the second row, first we try to write the place sign of each element just above the element. For writing the place sign, start with a positive sign for first element and then alternately minus plus only. So plus, here minus plus only. Now this is equal to, here only 2 elements are zeros, 2 elements are non-zeros only. So expansion of 1/4 order is just 2 third order determinants only. minus 1 into third order determinant plus 0 plus 3 into third order determinant. Its sign is minus plus 0 into something only. So if we expand directly along the second row, we require the two third order determinants. That is this 1 into third order, this 3 into third order only. Now without expanding these two third order also, we can add the value of the determinant using only one third order only. So to avoid one third order here, we try to make one of the element as 0 only. Along the second row, only 2 are zeros, 2 are non-zeros only. If we can make 3 as 0, or if we can make 1 as 0, we'll get 3 zeros only. After getting 3 zeros, in easy way, we can add the third order determinant value only. That is the advantage. So directly don't expand along the second row. Now we try to make one of the element as 0. Let us make this element as 0 only. So that we get the 3 zeros, and then we write directly the value of this by using only one third order only. If we have 3 zeros, directly expand. If we have only 2 zeros, then try to make other element as 0 so that we get 3 zeros only. Now to get 0 here, we apply the elementary operations only. We are expanding along the second row. For making the second row elements as zeros, we apply column operations. For row elements, apply the column operations. For making the column elements as zeros, apply the row operations. Along the second row, to make it 0, we use this element 1. That is this column minus this. So C3 position, C3 minus 3 times of C1. It is operation. But there is some condition to apply the operation on determinant. Now we are going back to that page. Now this is a condition. To apply the operation on determinant, strictly we follow this rule. Rj position, Rj plus Kri. Whatever the quotient is there here, but in place of this position, the quotient of Rj should be 1 only. Rj position, Rj plus Kri. This condition satisfies or not, we check it only. For columns, for rows, the position is Rj position, Rj plus Kri. Like this. Like this for columns also, Cj position, Cj plus Kci. These two should be same, its quotient should be 1. These two should be same, its quotient should be 1. Whatever the quotient here only. Now, is it in the form of this or not? Our operation is C3 arrow, C3 minus 3, C1. These two are same, its quotient is 1. So with this, the value of the determinant doesn't change. We can apply this operation, because this operation is in the form of like this only. So we are applying this operation along the third column position. We are subtracting first column from third column after multiplying the first column with the 3 only. So only third column will change. Other columns will be same only. 0, 1, 2, 3. 1, 0, 3, 0. Third column will change. Here third column is like this. 2, 3, 0, 1. Minus 3 times of first column. 3 into 0, 0. 3 into 1, 3. 3 to 6, 3, 3, 9. The difference of these two columns is 2 minus 0, 2. 3 minus 3, 0. 0 minus 6, minus 6. 1 minus 9, minus 9. So minus 1 minus 9, minus 8. 2, 0, minus 6, minus 8. And the last column is same. 3, 0, 1, 2 only. This is C3 minus 3 into C1. Difference of these two is this. Now we got 3 zeros along the second row. So we expand along the second row. If we expand this fourth order along the second row, we require only one third order only. Sign plus, minus, plus, minus, plus. But 3 zeros are there, not required. Directly we read this as along the second row we are expanding. So 1 into its sign, minus 1. Minus 1 into, delete the corresponding row, corresponding column, write the determinant of 3 by 3 matrix. That is 1, 2, 3, 3, minus 6, 1, 0, minus 8, 2, 1. Then write the value. So if we have only 2 non-zeros and 2 zeros, we try to make other element as 0 so that we get 3 zeros. If we get 3 zeros, directly 1 third order determinant value on. It is a 2 marks gate question. Now one for this. If we apply operations without operations also, we get same value only. That is why we are using the operation. If we use operations, we can avoid some third order determinant. In easy way we can find. What is the value of the determinant? What is the final answer for this? Now one of you got correct answer. Its answer is 88. It is a 2 marks gate question. So like this, we have the gate questions on 4 by 4 matrix with 2 elements are zeros, 3 elements are zeros along the row or column only. Directly 3 elements are zeros along the row or column, expand. That is same as 1 third order only. Suppose only 2 elements are zeros, 2 are non-zeros. Try to make one of the element as 0 using operation and write value of the determinant. For making column elements as zeros, for making the row elements as zeros, use the column operation. For making the column elements zeros, apply the row operations only. For column elements, use the row operations. For row elements, use the column operation. It is only difference. Right. Next, we go to the problem number 4. Fourth problem. Let capital A be a square matrix of order n minus 1, full stop. The elements of A are defined by Aij equal to n minus 1 for I equal to j minus 1 for I not equal to j. Full stop. The determinant of A is option A n power n minus 1, option B n power n minus 2, option C n minus 1 power n minus 2, option D n minus 1 power n minus 3. Now it is a given problem. Again, we are asked to find the value of the determinant. It is similar to first 3 problems. But first problem is third order, second problem is fourth order, Third problem is also fourth order. But here the fourth problem is we require the value of the determinant of n minus 1th order. In the fourth problem, we are given that n minus 1th order matrix. N minus 1th order matrix. For this n minus 1th order matrix, we require the determinant. Determinant of n minus 1 into n minus. Expansion of 1/3 order determinant is 3 second order determinants only. Expansion of 1/4 order is 4 third order determinants. Expansion of 5th order is 5 fourth order determinants. In general, expansion of n minus 1th order is n minus 1, n minus 2 order determinants. Is it easy to find directly? General order, not a particular order. Even the particular order, higher order is very difficult only. Here, general order is very difficult. So that is why don't find the determinant of this general order directly only. Try to choose the answer by verification only. Take the one particular order matrix, find its determinant value. With the help of that, choose the answer by verification only. We are given n minus 1th order, general order only. So let us choose the particular order matrix only. That is, in place of n minus 1, we choose some number only, particular number. That is n minus 1 equal to 3. Let us take the third order. Instead of n minus 1th order, take the third order. In every option, n minus 1th order determinant value is given. So let us find our third order determinant value and check the option satisfies with that third order determinant value or not. In this way, we can choose the answer. For general order, we try to choose answer by verification only. Otherwise, finding the determinant of general order is not an easy one. Okay, let us consider the particular order. Let n minus 1 equal to 3. Let n minus 1 equal to 3. N equal to 3 plus 1, 4. We are taking the third order matrix only. Now third order matrix equal to A equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Third order matrix. But this for n minus 1th order matrix, elements are not given directly. The elements are given indirectly by this formula. I equal to j means, for general element I equal to j means the two suffixes are same. That is aii or ajj. This is called diagonal element. And I not equal to j means the two suffixes are different. That is non-diagonal element. I equal to j. For all diagonal elements, element is like this. For all non-diagonal elements, elements are like this only. So I not equal to j, non-diagonal elements is fixed on. That is minus 1. But for diagonal elements is n minus 1. For n minus 1th order matrix, diagonal elements are order only. Other elements are minus 1. So here diagonal elements are, it is a 3 by 3 matrix. So 3 minus 1 minus 1 minus 1 3 3. So this is minus 1 minus 1 minus 1 3. Where aij equal to 3 for I equal to j minus 1 for I not equal to j, because according to this formula n minus 1 is, our n minus 1 is 3 only. So diagonal elements are 3, non-diagonal elements are minus 1, which implies determinant of A3 by 3 matrix equal to. If we expand and simplify, then the determinant of A is equal to What do you get here? 16. Check where it is 16 or not. Right. If we expand and simplify, this will be 16. So for determinant of A3 by 3 equal to 16, then for n minus 1 order, what is the value? Now see this. Here for n equal to 3, sorry, any n minus 1 equal to 3 or n equal to 4, it is the value only. Determinant of A3 by 3 equals 16 for n minus 1 equal to 3 or n equal to 4 only. Now in every option substitute, n equal to 4, n minus 1 equal to 3 and check any one of the option satisfies with this value or not only. In the first option, n power n minus 1, if we substitute n equal to 4, n minus 1 equal to 3, then this becomes 4 power 3 only. 4 power 3 is not equal to 16. So the first option is not satisfied to 16 for n equal to 4 only. So A is wrong. Next, second option, n power n minus 2, n equal to 4. Next, n minus 2, n equal to 4, 4 minus 2, 2, 4 power 2, 16. The second option is satisfied. Even though second option satisfies with this value, don't choose this as correct answer because more than one option may satisfy only. So let us go to the next one. N minus 1 equal to 3, n minus 2 equal to 4 minus 2, 2, 3, 3, 9. Our value is 16. So third option is not satisfied with this. Next option D. N minus 1 equal to 3, n minus 3, 4 minus 3, 1 equal to 3, and not same as 16. So when you substitute n equal to 4 or n minus 1 equal to 3, only second option will give the 16. So that is why second option is correct only. Therefore, determinant of n minus 1 by n minus 1 equal to n into n power n minus 2 only. So it is the answer. Whenever general order problem is given like this, try to choose answer by verification. For verification, let us choose a particular order, try to find that value and choose answer from the options. It is a method. This is problem number 4. Next, we go to the problem number 5. We can choose a 2 by 2 matrix, 3 by 3 matrix, 4 by 4 matrix, any one we can choose, no problem. Because in the problem itself, the condition is not given. If you are given condition n greater than 2 or n greater than 3 or n greater than or equal to 3, like the condition is given, according to that condition, we can choose a particular order. Here condition is not given, means we can choose any order only. So better to choose it second order or third order only. Next, problem number 5. If A is M cross N matrix and B is N cross P matrix, then the number of multiplications the number of multiplications and additions. Then the number of multiplications and additions involved in computing the matrix product AB or option A, MNP MNP plus 1, option B, MN minus 1 P comma MNP plus 1. Option C, M minus 1 NP comma MNP. Option D, none of these. It is a problem. It is a gate question. If A is M cross N matrix and B is N cross P matrix, then the number of multiplications and additions involved in computing the matrix product. Suppose A is M cross N and B is P cross Q only. For given two matrices, we may or may not find the product only. That is, for given two matrices, the product may or may not exist only. To find the product of two matrices, there is some condition. If A is M cross N, B is P cross Q, for the existence of this product AB, the condition is inner dimensions should be same. These two inner dimensions should be same, or inner orders should be same only. If we have any doubts, we can ask the doubts at the end of the class. I clarify your doubts at the end of the class. Just write the doubt on paper and later you ask me. So if A is M cross N, B is P cross Q, then the product will be possible whenever inner dimensions are same or inner orders are same. A is M cross N matrix, B is P cross Q matrix, N equal to P, N equal to P. That is, inner dimensions are same, then we can get the product matrix. The resulting matrix order is outer dimensions, outer orders, M cross Q matrix. N equal to P, product is possible, then we can have the matrix. Now here the product is possible or not only. Product is not possible, directly none will be correct answer only. Product is possible, one of the first three options will be correct. First three are also wrong, none may be correct also. Here A is M cross N matrix, B is N cross P matrix. Inner dimensions are same. When inner dimensions are same, inner orders are same, product exists. The resulting matrix order is M cross P only. The total number of elements in AB matrix is M into P, MP elements only. To find these MP elements, we require some calculations. The calculations will involve both products and sums only. We require that product operations, number of product operations, number of addition operations only. So for this problem, because here we are given general order, so let us consider the particular order and we try to find the number of multiplications, additions for particular order matrix. After that, we generalize directly for any order. Let us consider particular order matrix, A 2 by 3 matrix, 1, 2, 3, 4, 5, 6. 2 by 3 matrix, comma, B equal to 3 by 4 matrix, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 3 by 4 matrix. A is 2 by 3, B is 3 by 4. For both matrices, inner dimensions are same, so product exists. The resulting matrix order is 2 by 4 or 2 cross 4 on. Now AB matrix equal to 2 by 4. That is 2 rows, 4 columns. Along the first row, 4 elements. Along the second row also 4 elements. 1, 2, 3, 4. 1, 2, 3, 4. 2 into 4, 8 elements, or 4 plus 4, 8 elements only. To obtain these elements of AB matrix, we choose something from first matrix, we choose something from second matrix. After that, we do something, we get something, we write something. Now, what do you require? Suppose if you want to find the very first element, if you want to find the first element, to find the first element of this matrix, we require the first row from first matrix and first column from second matrix. By choosing the first row and first column from A and B, we try to get the first element of this matrix only. After choosing the row and column, we consider corresponding elements, product, and their sum only. Corresponding element. Corresponding element. Corresponding elements. First elements product. Next, second elements product. Third elements product. Now, to find the first element of this matrix, we require the product of these two, product of these two, product of these two only. That is like this: 1 into 7 plus 2 into 11 plus 3 into 15 only. How many products here? 1, 2, 3. 1, 2 only. 3 multiplications, 2 additions only. So to obtain the one element of this matrix, to get first element of this matrix, we require the 3 multiplications. How many multiplications? 3. How many additions? 2 only. So of this required matrix AB, we require 3 multiplications and 2 additions for all elements for one element, multiplications is given by, for one element, number of multiplications is 3. Like that, for all 8 elements, 8 into 3 equal to 24. 24 multiplication operations. Similarly, number of additions. For one element, 2 additions. For all 8 elements, 8 into 2 equal to 16. Number of multiplication operations and this number of addition operations are required to obtain the 8 elements of AB matrix. 8 elements of AB matrix only. Okay. This is the method only. So to obtain each element, we require the 3 products and 2 additions. Like that, for 8 elements, 24 multiplications and 16 additions only. It is a method. Now we can generalize for this. Okay. Look at this. For one element, number of multiplications is 3 only, because we have 3 elements along the row, 3 elements along the column. Whenever the number of elements along the row is same as number of elements along the column, then only the product is possible only. Because of 3 elements along the row, 3 elements along the column, we require the 3 multiplications. From this, we can say that number of multiplications for one element, number of multiplications for one element is same as number of elements along the row or column, or that is also same as number of multiplications for each element is same as inner order, inner dimension. When these two are same, then only product is possible. That is same as this. For each element, number of multiplications is same as inner dimension 3. For each element, number of additions is inner order minus 1. Also remember that here, number of additions is 1 less than number of multiplications only. Number of additions is 1 less than number of multiplications only. For each element, number of multiplications is inner dimension. For each element, number of additions is inner dimension minus 1. That is 3 minus 1, 2 only. Inner dimension minus 1. Now we can generalize this same thing for any number of matrices only. But here we have to find the only for product of 2 matrices. Okay. Let us try the for general matrix only. Here we are given that A is M cross N matrix, comma, B is N cross P matrix. Now between these two product is possible because inner dimensions are same. So product exists. The resulting matrix is of order N cross P. The resulting matrix order is N cross P only. The total number of, sorry, this is M cross P. The total number of elements is MP only. Now for one element or for each element, number of multiplications is same as inner dimension n. For each element, number of multiplications is same as inner dimension n. For the same one element or for each element, number of additions is inner dimension minus 1. Like that for all MP elements only. For one element, number of multiplications is n. Number of additions is n minus 1. Like that for all elements. Total number of elements is m into p only. For one element, n multiplications. For MP elements, mp into n. For one element, n minus 1 additions. For MP elements, mp into n minus 1. So this gives MPN, this number of multiplication operations, this number of addition operations. So to find the MP elements of this AB matrix, according to these orders, we require MPN multiplication operations, MPN minus 1 addition operations. So are these two given in the options or not? Check it only. MPN minus 1. That is not there. So answer is D only. Okay. So for any order, directly we can tell the answer. For example, if A is 4 by 3 matrix, comma B is 3 by 5 matrix. Here inner dimensions are same, so the product AB exists. The resulting matrix order is 4 by 5. The total number of elements in this matrix is 4 into 5, that is 20 elements only. The number of multiplications, number of additions are required. Number of multiplications is same as total number of elements into for each element number of multiplication. For any order matrices in the product of two matrices, number of multiplications for each element is inner dimension, that is 3. For one element, 3 multiplications. Like that, for all elements, the number of multiplications is 4 into 5, 20, 23, 60 multiplications on. Total number of elements is 4 into 5. For each element, number of additions is n minus 1. That is 3 minus 1 here. So 20 into 2, 40. This number of multiplications and additions are required. Order the product is possible. Directly we can tell the number of multiplication operations and number of addition operations. See this total number of elements 4 into 5 into inner dimension is number of multiplication operations. Total number of elements into inner order minus 1 is the number of addition operations directly on. Right. Now this is about problem number 5. Okay. Most of them are asking break. Okay, we'll take the break. Okay, let us take the break. We'll take the break 15 minutes, 5 minutes. After 15 minutes, we start. Okay, all right. Let us take the break. Okay, let us start our class. The break time 15 minutes is completed. Now we go back to our class. Now till now we have done problem, that is, till now we have done the 5 problems. Now after these problems, we'll discuss about the properties of determinants. After the properties of determinants, we go to next subtopic. Properties of determinants. Here I won't write the properties of determinants in written form. If we have a standard result, we write the standard result for the property. If we don't have the standard result, by taking the example, we'll discuss about the property only. Okay, let us start with the first property. Determinant of A n cross n into B n cross n equal to determinant of A n cross n into determinant of B n cross n. Determinant of product of two matrices equal to product of their individual determinants only. So determinant of product equal to product of individual determinants only. This is the first property only. Next, property number 2, determinant of A power k equal to determinant of A power k. The power of A is same as power of determinant only. For all k belongs to capital N. Capital N means set of all natural numbers. This property works only for positive integers. For negative integers also, we can add this property, but with some condition. We write that as a note point. Note point number 1. Determinant of A power k equal to determinant of A power k for all k belongs to I means set of all integers such that determinant of A not equal to 0. It is a condition. For negative integers also, we can add this power of A as power of determinant when determinant is not equal to 0. But here, for all positive integer powers, determinant of A power k equal to determinant of A power k on. Next, property number 3, determinant of A power t equal to determinant of A. If A is a matrix, then A power t is the transpose matrix of A only. Transpose matrix means if you interchange the rows into columns, then the resulting matrix is called. If you interchange the rows into columns, columns into rows, then the resulting matrix is called transpose matrix of A only. So from this property, we can say that the determinant of A is same as determinant of its transpose. That is A and A transpose. A and A transpose will have same value. That is, both will have the same determinant value on. Fourth one. 1, 2, 7, 0, 0, 0, 3 minus 1, 4 equal to. What is the value for this? 0. If any single row is a 0 row, or if any single column is 0 column, then the determinant is always 0. Along any row or column, all the elements are zeros, then such a row is 0 row or 0 column. So one of the row is 0 row or one of the column is 0 column, determinant value is always 0. Fifth one. 1, 2, 3, 4, 7, 5, 1, 2, 3 is equal to 0. The reason for this is the first and last rows are same. When two rows are same, in a determinant, then the value of the determinant is 0. 1, 3, 7, 2, or we read this 2, 6, 14, 11, 5, 6. Its value is also 0. The reason for this is the two rows are proportional only. The first and second rows are proportional or multiples only. When two rows are same or when two rows are proportional or multiples, then the value of the determinant is 0 only, because second row is 2 times of first row. If any row is 0 row, determinant is 0 only. If any two rows are same, determinant is 0. If any two rows are proportional, determinant is 0 only. Next, property number 6. One, 2, 3, 4, 5, 6, 7, 8, 0. I am taking the one third order determinant. It's after expansion, its value will be 27. If we expand this, its value will be 27. Now here, I am interchanging the rows. First to last, last to first. 7, 8, 0, 4, 5, 6, 1, 2, 3. First row is interchanged with the second, last row only. When two rows are interchanged only, the value of the determinant will be multiplied with -1. If we interchange the two rows once in a determinant, the determinant will be -1 only. From this, we can set for one time of interchange of two rows, in a determinant, the sign changes. Suppose if you do one more time, that is if you interchange one more time, 7, 8, 0, 1, 2, 3, 4, 5, 6 equal to. Again, for one more time of interchange of two rows, this is equal to -1. Its previous value is -1 into 27. This is equal to. This is obtained from the first one after one time interchange of two rows. So 1 minus 1. This is obtained from the first one after two times of interchange of two rows. That is why 2 minuses only. 2 minuses even number of times. 1 minus 1 odd number of times only. Minus 27 plus 27. From this we can set, if we interchange, if we rows once, then sign changes. If we interchange the two rows once in a determinant, the sign changes only. Even number of times plus, odd number of times minus, that's all. Next, seventh property. K into determinant of 1, 2, 3, 4, 5, 6, 7, 8, 0. This is equal to K, 2K, 3K, 4, 5, 6, 7, 8, 0. 1, 2, 3, 4K, 5K, 6K, 7, 8, 0. Or 1, 2, 3, 4, 5, 6, 7K, 8K, 0K. Or 1K, 2, 3, 4K, 5, 6, 7K, 8, 0. Or 1, 2K, 3, 4, 5K, 6, 7, 8K, 0. Or 1, 2, 3K, 4, 5, 6K, 7, 8, 0K. Now observe this. We are multiplying some scalar with a determinant. If you want to multiply something with a determinant, then we should multiply that with any one row or any one column. We should not multiply that K with every row or every column only. So we can multiply K with the first row, second row, third row, first column, second column, third column only. Reverse. Reverse is like this. In a determinant, along the row, all the elements are multiplied with some scalar. We can take the scalar directly outside. From a single row, we can take the scalar directly outside. Or along any column, all the elements are multiplied with a scalar. We can take the scalar directly outside. It is the result. So multiplication of a row by scalar on. Note point. Determinant of K into AN cross N equal to. Okay, we write a note point number 2 as this. Before this, we write another note point. K into 1, 2, 3, 4, 5, 6, 7, 8, 0. This is equal to K, 2K, 3K, 4K, 5K, 6K, 7K, 8K, 0K. Now, if we compare this note point 1 with the above, there is some difference. In note point 1, this is a matrix only. If you want to multiply scalar with the matrix, then we should multiply scalar with every element of the matrix or with all rows or columns only. It is a difference. If you want to multiply scalar with a determinant, we should multiply scalar with only one row, one column. But here matrix means we should multiply every element with a constant. And this matrix is called scalar multiple of matrix. We are obtaining this matrix from the product of these two only. That is, we are multiplying scalar with the matrix. The resulting matrix is called scalar multiple of matrix only. Note point number 2, determinant of K into AN cross N equal to K power N into determinant of AN cross N. Now K into AN cross N means scalar multiple of matrix. This is the matrix only. If you take the determinant of this, matrix, from each row we can take one K outside. K into K into K, K cube into determinant of A only. So determinant of K into AN cross N equal to K power order of the matrix into determinant of A only. Next, property number 8. Eighth property. One, 2, 3, 4, 5, 6, 7, 8, 0 equal to 1 plus 4K, 2 plus 3K, 4. So this is 2 plus 5K, 3 plus 6K, 4, 5, 6, 7, 8, 0. Now observe this. On left hand side, the value of the determinant is 27, but this determinant equal to determinant is written. This determinant equal to determinant means both will have the same value. Whatever we have the value of this determinant, that will be same as the value of this right hand side only. But when you compare the right hand side determinant with the left hand side, there is some change along the first row. On right hand side, there is some change along the first row. That is 1 plus 4K, 2 plus 5K, 3 plus 6K. That is second row is multiplied with the scalar K Second row is multiplied with the scalar k added to the corresponding elements of first row only. So here one operation is applied. The operation is along the first row position. Along the first row position, R1 plus K into R2 only. Second row is multiplied with this. Second row is multiplied with the scalar k added to the corresponding elements of first row only. It is a operation. This is in the form of third elementary operation out of three elementary operation. The last operation is Rj position Rj plus Kri. Rj position Rj plus Kri. Here these two are same, its quotient is 1. Then the value of the determinant doesn't change. That is why here the value of this is same as value of this only. If you observe the property number 6, 7, 8, the property number 6, 7, 8 are same as the three elementary operations. In property number 6, interchange of two rows. Property number 7, multiplication of row by scalar. In property number 8, multiplication of row by scalar adding to some other row with the corresponding elements. So property number 6, 7, 8 are the same as three elementary operations on determinant. The first elementary operation changes the sign. Second elementary operation changes the value. Only third operation doesn't change the value. That is why while expanding the higher order determinants to make some elements as zeros, we use this elementary operation. We use this elementary operation. While expanding higher order determinant values, we make some elements as zeros using this elementary operation. That is why elementary operations are required for expanding the higher order determinant. Right. This is property number 8. Next, property number 9. In the ninth property, we write the 3 by 3 matrices and their determinant values on A equal to A, B, C, 0, D, E, 0, 0, F. Now this matrix is upper triangular matrix only. This is called upper triangular matrix. In a square matrix, all the elements below diagonal are zeros. In a square matrix, all the elements below diagonal are zeros. Then such matrix is called upper triangular matrix. Or other way, upper present, then upper triangular matrix. Which implies determinant of A equal to product of diagonal element. So determinant of upper triangular matrix is product of its diagonal elements. A 0 0, B C 0, D E F. Determinant of A equal to A into C into F. A into C into F. It is a lower triangular matrix. In a square matrix, all the elements above diagonal are zeros. Then the matrix is lower triangular matrix. Its determinant is product of diagonal elements. Next, A equal to A 0 0 0, B 0 0 0, C. A into B into C. In a square matrix, all the elements above, below, diagonal. In a square matrix, all the elements above the diagonal, below the diagonal elements are zeros. All the elements above diagonal, below diagonal elements are zeros. Then such a square matrix is called diagonal matrix. Above the diagonal, below the diagonal, all the elements are zeros. The matrix is diagonal matrix. Its determinant is product of diagonal elements. K 0 0 0, K 0 0 0, K. In this matrix also, all the elements above the diagonal, below the diagonal elements are zeros. So it is a diagonal matrix, but all diagonal elements are same. So it is a scalar matrix. Determinant of scalar matrix equal to product of diagonal elements. Equal to K cube. A equal to 1 0 0 0 1 0 0 0 1. In the matrix, all the elements above, below are zeros, diagonal matrix. All diagonal elements are same. So scalar matrix. But in particular, all diagonal elements are equal to 1. Then unit matrix or identity matrix. Its determinant is product of diagonal elements equal to 1. A equal to 0 0 0 0 0 0 0 0 0. It is zero matrix or null matrix. Determinant of the matrix is 0. From all these, we can set determinant of upper triangular matrix, lower triangular matrix, diagonal matrix, scalar matrix, unit matrix, zero matrix is equal to product of its diagonal elements. For all these matrices, determinant is product of its diagonal elements. Next, property number 10. A1 plus x1 plus y1. A2 plus x2 plus y2. A3 plus x3 plus y3. This is the first column. Second column is B1, B2, B3. Third column is C1, C2, C3 equal to. When you compare first column with other columns, in second, third column, only single element only. But in the first column, element is sum of 3 numbers. Every element is sum of 3 numbers. Along any column, every element is sum of 3 numbers. Then we can write the determinant as sum of 3 determinants. Based on this first column element, we are writing the determinant as sum of 3 determinants. Or if any row is a sum of 3 numbers, we write the determinant as sum of 3 numbers. That is sum of 3 determinants. For all 3 determinants, the second and third columns are fixed. Only the first column will change. Determinant plus determinant plus determinant. Along the first column, every element is sum of 3 numbers. That is why we can write the determinant as sum of 3 determinants. But last 2 columns are same. B1, C1, B2, C2, B3, C3. For every determinant, same. B1, C1, B2, C2, B3, C3 on. B1, C1, B2, C2, B3, C3. Only the first column will change. Now from the first column, we take the first numbers in the first determinant. A1, A2, A3. Second numbers. X1, X2, X3. Here Y1, Y2, Y3 like this. So if any column is a sum of 3 numbers, then we write the determinant as sum of 3 determinants. Or if any column is sum of 2 numbers, then determinant will be written as sum of 2 determinants like this. These are the properties of determinants. With this property, the first subtopic, determinant of a matrix, is completed. So in the first subtopic, determinant of a matrix, we have seen the methods of finding the determinant of second order, third order, fourth order. Whatever we have the method for fourth order, we apply the same method for next higher order determinants. That is the general method. And then we have done problems. After that, we have seen the properties of determinants. With this, the determinants topic is completed. Now we go to the next subtopic, that is inverse of a square matrix. Inverse of a square matrix. In this subtopic, we will discuss the method of finding the inverse of a square matrix. We'll discuss about the method of finding the inverse of a square matrix. Now, to find the inverse of a square matrix, we have many methods. Very first method is adjoint method. That is, using adjoint matrix, we can add the inverse of a matrix. Next, Gauss-Jordan method. Next, diagonalization method. Next, Cayley-Hamilton theorem. Like this, we have many methods to find the inverse of a square matrix. But here, we'll discuss about the method of finding the inverse of matrix by using adjoint method only. For this, we should know the minor of element, cofactor of element, then cofactor matrix. After that, we write the adjoint matrix. So let us write all these, and then we go to the inverse. This first one, minor and cofactor of an element. Minor and cofactor of element. Minor and cofactor of element. If A equal to Aij n cross n is a square matrix, then the first bit, minor of an element Aij is capital Mij. This is equal to n minus 1th order determinant. Which remains after deleting the corresponding ith row and jth column in an cross n matrix. So to find the minor of the element, again we require the determinant. For nth order matrix, minor of each element is its immediate lower order determinant, n minus 1th order determinant. And to obtain this n minus 1th order determinant, we should delete the corresponding ith row and jth column in the nth order matrix. If you know the minor, we can add the cofactor of element. The second one, the cofactor of an element Aij is capital Aij equal to minus 1 whole power I plus j into Mij. This is a cofactor. So just multiply the minor of the element with its sign, place sign. Then that product will give the cofactor of element. Now we read the example for this. Let us consider 3 by 3 matrix with elements 1, 2, 7, 4, 3, 5, 0, 6, minus 1. It is the 3 by 3 matrix. Now let us find the minor and cofactor of some elements. First, we try to find the minor and cofactor of this position only. This belongs to second row, position is 8, 2, 3 only. Here, 8, 2, 3 equal to 5. For this element, the minor is given by Mij, that is minor is denoted by M23. It remains after deleting second row and third column. When you delete the second row, third column in the 3 by 3 matrix, we can obtain 2 by 2 matrix. For that, determinant is 1, 2, 0, 6. Determinant of this is 6 minus 0, 6. It is the minor of the element. If you know the minor, we can add the cofactor. It is denoted by capital A23. This is equal to minus 1 power 2 plus 3 into M23 equal to M23 is plus 6 minus 1 power odd power. So minus, this is minus 6. This is the cofactor of this position A23 only. Next, we try to find the minor and cofactor of other position 0. For this 0 belongs to third row, first column. That is, its position is A31. And for A31, it's 0. For this element, the minor is denoted by M31 equal to, delete the corresponding row, corresponding column. M31 equal to, if you delete the last row, first column, the leftover determinant is 2, 7, 3, 5 equal to minus 11. And its cofactor is A31 equal to minus 1 power 3 plus 1 into M31 equal to minus 1 power even power, then becomes plus, but M31 is already minus 1, so its cofactor is minus 11. Like this, we can find the minor and cofactor of each element. If you know the cofactors of each element, by using the cofactors, we can write a new matrix. Such a matrix is called cofactor matrix only. That is next one. Cofactor matrix. If capital A equal to A11, A12, A13, A21, 22, 23, A31, A32, A33. 3 by 3 matrix. Then the matrix in the matrix capital B equal to, that is, we write a new matrix by replacing each element in the given matrix with their corresponding cofactor. That is, in the given matrix, for every element we find the cofactor. Using the cofactor, we write the new matrix. Such a matrix is called cofactor matrix. Now for A11, corresponding cofactor is denoted by capital A11. For A12, corresponding cofactor is capital A12 and so on. A33, corresponding cofactor is A33. Replace each element in the given matrix with their corresponding cofactors and form a new matrix. The new matrix is A11, A12, A13, 21, 22, 23, 31, 32, 33, comma, where capital Aij equal to minus 1 whole power I plus j into Mij is a cofactor matrix of matrix A3 by 3. This is the cofactor matrix. Next, third one, adjoint matrix. If B n cross n is a cofactor matrix of a matrix A3 by 3, then adjoint matrix, the adjoint matrix of A3 by 3 matrix, the adjoint matrix of A3 by 3 matrix is denoted by small a, small d, small j, adj, after this within the brackets a, and defined as adj of a equal to b power t only. If B is the cofactor matrix, its transpose is the adjoint matrix. In the above, A is the cofactor matrix and A is the given matrix, B is the cofactor matrix only. This B is the cofactor matrix of A only. So if you take the transpose of this, that is B transpose is the adjoint matrix of this. Next, fourth one. Singular matrix. The condition for singular matrix is determinant of A n cross n equal to 0. For any square matrix, after finding the determinant, the value is 0, then such a square matrix is called singular matrix. It is a condition for singular matrix. Next, non-singular. Non-singular matrix. The condition for non-singular matrix is determinant of A n cross n not equal to 0. Condition for singular matrix is determinant equal to 0. Condition for non-singular is determinant of a not equal to 0. Next, sixth one. Inverse or reciprocal of a square matrix. If AB equal to BA equal to IN for determinant of AN cross N not equal to 0 and determinant of BN cross N not equal to 0. If AB equal to BA equal to IN, then for non-singular matrices, then BN cross N is the inverse of a matrix AN cross N, and it is denoted by A power minus 1. So this condition satisfies. Take the two non-singular matrices, find the product AB, BA, and check whether they are equal or not. Both are equal, and both are equal to unit matrix or not. Both products AB, BA equal to unit matrix, then the matrix B is the inverse of A. If B is inverse of A, then A is also inverse of B, inverse to each other only. Next, note points. Note point number 1. If determinant of AN cross N not equal to 0, then A inverse equal to, according to adjoint method, inverse is given by something in the numerator adjoint of A, in the denominator determinant of A. Now it is the formula to write the inverse of a square matrix according to adjoint method. We have to find the determinant, and we have to check whether it is 0 not equal to 0. Determinant is not equal to 0. We write the inverse matrix. If we have something by something, for the existence of this ratio, denominator part must be not equal to 0 only. So it is also in the form something by something. For the existence of this ratio, denominator part must be not equal to 0. First of all, denominator is determinant. The determinant is not equal to 0, the ratio is possible, then inverse is possible. Determinant is 0, ratio is not possible, inverse is not possible. That is why for non-singular matrices, inverse exists. So not equal to 0, non-singular, inverse exists. Inverse exists. The matrix is called invertible matrix. Invertible matrix only. A inverse exists. Such a matrix is called invertible matrix only. Next, note point number 2. If A equal to 2 by 2 matrix A, B, C, D, then A inverse equal to adjoint of A divided by determinant of A equal to now for this 2 by 2 matrix, determinant is AD minus BC, product of diagonal elements minus product of non-diagonal, AD minus BC into 2 by 2 adjoint matrix. Again, to write the adjoint matrix for each element, we write the minor cofactor. Using cofactors, we form a matrix, and by taking the transpose, we write the adjoint matrix. That is a method. But for this 2 by 2, directly we write the adjoint without finding all these. Just interchange diagonal elements A to D, D to A, and take the minus sign for non-diagonal elements, minus B, minus C. It is A inverse for 2 by 2 matrix. Next, note point number 3. point number 3. If A is any square matrix of order n, then the first result A into adjoint of A equal to adjoint of A into A equal to determinant of A into IN. A into adjoint equal to adjoint A into A equal to determinant of A into IN. The second result, determinant of adjoint of AN cross N equal to determinant of A power N minus 1. Third result, adjoint of AN cross N equal to determinant of A power N minus 1 power 2 only. Like this, we can add any number of times of adjoint. If you observe the second and third result on right hand side, observe the results. From second and third on right hand side, determinant n minus 1, their powers are different. The power of n minus 1 is same as number of times adjoint inside the determinant only. If we have a 3 adjoint, then determinant of A power n minus 1 power 3 only. The power of n minus 1 is number of times adjoint inside the determinant. These 3 results for any order square matrix, that is, the matrix may be singular or non-singular, doesn't matter. These 3 results hold for both matrices. Next, note point number 4. If determinant of AN cross N not equal to 0, then the first result is adjoint of AN cross N equal to determinant of A into A inverse. Already we have the formula A inverse equal to adjoint of A by determinant. From this, write the adjoint equal to determinant of A into A inverse. And the second result, adjoint of AN cross N equal to determinant of A power N minus 2 into A. These two matrices are possible for non-singular matrix only because A inverse. Next, note point number 5. Note point number 5. A equal to Aij for this square matrix, we read the 3 matrices conditions. A transpose equal to A, or Aij equal to Aji. This condition satisfies for any square matrix. Such a matrix is called symmetric matrix. A transpose equal to minus A, or Aij equal to minus Aji. Same as above, but minus sign. This is called skew symmetric matrix. Next, A into A transpose equal to A transpose into A equal to IN, or A inverse equal to A power D transpose. Then this matrix is called orthogonal matrix. Orthogonal matrix. So we have written the three types of matrices conditions. A transpose equal to A symmetric, A transpose equal to minus A skew symmetric, A into A transpose equal to A transpose into A equal to IN. If AB equal to BA equal to IN, then B is the inverse of A. If B is the inverse of A, then A is also inverse of B1. In place of B, that is in place of B, here we have the A transpose. So A into A transpose equal to A transpose into A equal to I, then the matrix is called orthogonal matrix. If A is orthogonal, its inverse is given by just transposal. So inverse of orthogonal matrix is just its transpose. You will don't copy this. If you are able to copy within the time. If you are unable to copy, don't worry about this. But note it down this. Even if you are unable to copy also, even if you are unable to write this also, no problem. Because this PDF copy will be given to you only. Don't worry about this. Don't take screenshot also. You will be given this class PDF. Now for each we write the example here. One, 2, 4, A11, A12. According to symmetric matrix condition, A12 equal to A21. If it is A1, if A12 equal to 2, then A21 is also 2 only. 8. A13 equal to 4. If A13 equal to 4, then A31 is also same. If it is minus 5. This is the position A23. If A23 equal to minus 5, then A32 also minus 5. Then A33 may be any number. These two are same. These two are same. These two are same only. So whatever we have the elements above the diagonal, we have the same elements below the diagonal also. Whatever we have the elements above the diagonal, we have the same elements below the diagonal. So diagonal above diagonals may be different. So the maximum possibility for number of different elements is 3, 2, 1. Totally 6 only. Along the first row 3, along the second row 2, along the first row 1. These are the possibilities for maximum number of different elements only. It is a symmetric matrix. Next, example number 2 for skew symmetric. A equal to here Aij equal to minus Aji condition. If we substitute j equal to I, then Aii equal to minus Aii. Then 2Aii equal to 0. Aii equal to 0. From this, we can say that diagonal elements of a skew symmetric matrix are always 0 only. Zero, 2, minus 3. If A12 equal to 2, then A21 will be minus 2, 0. If A13 equal to minus 3, then A21 equal to negative 1, minus of this, that is becomes plus, minus 4, 0. These two are same, these two are same, these two are same, but opposite sign only. These two are same, opposite sign. These two are same, opposite sign. These two are same, but opposite sign. But diagonal elements are always zeros. In a skew symmetric matrix, diagonal elements are always zeros. Next, third example of orthogonal matrix. 1 by root 2, 0, 1 by root 2, 0, 1, 0, minus 1 by root 2, 0, 1 by root 2. It is orthogonal matrix. Examples of these. Next, last note point. Note point number 6. Every odd order determinant, every odd order determinant of a skew symmetric matrix is always 0. Odd order means first order, third order, fifth order, seventh order, and so on. These order skew symmetric matrices are always singular because its determinant is always 0. Every odd order determinant of a skew symmetric matrix is always 0. That's all. These are the 6 note points. Now we close the today's session. Tomorrow, that is in the next class, we do the problems on this. After completion of this, we try to start the rank of a matrix. After doing the problems on inverse of matrix, we start next subtopic rank. Also, one of you asked the LU decomposition. LU decomposition is not a particular subtopic only. LU decomposition is one method to find the solution of system of linear equation. That is why I did not write the LU decomposition as a subtopic only. LU decomposition is just one method to write the solution of the system of linear equation. That's it. That is also included. We discuss about that at the end of the topic. Okay, we'll discuss some doubts because some of you are asking doubts. Now today's class is completed. Today's class is completed. If you have doubts, we can ask the doubts. If you don't have doubts, we can take rest. Okay, let us discuss about the doubts. Hello. Hello.
Sir, can you hear me?
You can ask.
Sir, yeah, sir. Sir, like number of multiplications and addition problem, no, sir. Like, can we use any other mathematical method to reduce those numbers? Like, can we reduce those multiplications and additions by using any other way, or those formulas are fixed?
Oh, that is fixed only. We cannot reduce the number of multiplication, but we can suppose if we take the three matrices only, A, B, C only. Okay. If we have only two matrices and if we want to find the product AB, we can find the product AB only in one way only. We can find the product only in one way. But if you want to find the product ABC, we can find the product in two ways. One way is AB into C, other way is A into BC. Like this, we can reduce the number of multiplications only. Number of additions, operations.
Okay. Yeah, okay, sir.
With the
Got
minimum
it, sir.
number of
So
multiplications,
when
we can calculate fast.
yeah, sir, then the same formulas we can apply for three also, no, sir? Like
Same formula.
first
Same
we have
formula.
to take two and then we have to apply, sir. Okay, sir. Thank you,
Right.
sir.
Okay. Next. Hello. Hello. Hello.
Good evening, sir. Am I audible?
Yeah, you're audible.
Sir, in the question that we found out the number of multiplication and addition operations for the product of matrix,
Okay.
the common generalized formula for addition operation is m into n into p minus 1, right?
Yeah. No,
Sir,
n minus. Suppose. If I take the A m cross P and B P cross N like this, suppose.
Okay.
Inner orders are same, product exists. The resulting
Yes.
matrix is A, B is of order M cross N. Total number of elements is Mn. So number of multiplications is same as the total number of elements Mn into inner dimension P. Okay. Number of additions is total number of elements Mn into inner order minus 1, P minus 1. That's all.
Okay, sir. Okay, thank you, sir.
That is Mn into P multiplications. Mn into P minus 1 is additions.
Okay, sir.
Okay, right.
Yeah, thank you.
Hello.
Sir, if we want to find the determinant of a matrix and there aren't enough
Determinant of which
if
one?
we want to find the determinant and there are not enough zeros in any row, then if we apply row operation on row and make extra zeros, then the determinant is the same, right?
Right. Some elements are not given as zeros.
Yes, sir.
Then we can make some elements as zeros and we can write the value of the determinant also.
Okay. Thank you, sir.
Anybody's there? Hello.
Good evening, sir. Am I audible, sir?
Yeah, you are audible. You can ask.
Sir, can you move to the eighth note point of previous, like 1 plus 4k, 1 plus that,
Yeah. Property.
yes, that property.
This one, eighth property.
Yes, sir. This one only for determinant we need to do, sir. If with matrix, this is not possible.
No. Matrix also possible. Matrix means we can use any one. For matrix, we can apply like this also. R1 position, R1 plus K R2, or R1 position, R1 plus K R2, and we can multiply R1 also with some other scalar.
Okay, sir.
For matrix,
okay.
we can apply both one. But for
Sir,
determinant
just
only
to-
one operation.
Okay, sir. This is done just to reduce the matrix, sir.
Actually,
Row operation.
to find the higher order determinant values, we try to make some elements as zeros.
Okay.
To make some element zeros, we apply this type of elementary operation.
Okay, sir. Sir, can you move to inverse of a square matrix, sir? Like it's like a 15 or 16th slide.
This one, I think. Is it correct?
No. Inverse of a square matrix, sir. Like Mij minor of an element.
Okay, first one.
That one I didn't understand, sir. Means I went on a confusion. Like.
Okay. Suppose if
yes, sir. Yes, sir.
If A is n cross n matrix, for this n cross n matrix, for each element, minor is denoted by Mij. This minor is defined as n minus 1th order determinant.
Okay.
Minor of the element Aij of this matrix is denoted by Mij, defined as n minus 1th order determinant. To obtain this n minus 1th order determinant, we delete the corresponding ith row and jth column. In this nth order matrix, if we delete one row, one column, we can obtain the n minus 1th order matrix. For that n minus 1th order matrix, we find the determinant.
Means like for suppose here we took 5 now, sir. Means like corresponding elements we need to remove, right?
Yeah. Suppose
1, 2,
5 belongs to which position? Second row, third column. Its position is 8 to 3. Okay. For this element, if you want to find the minor, that is denoted by M23. And if you want to write the determinant, then we delete its corresponding second row and corresponding third column. So that we can write the determinant of 2 by 2, 1, 2, 0, 6. That is a minor.
Okay, sir. Here, sir, A23 is what, sir? That is for cofactor, sir?
No. A23 is the element position.
Down. Minus 6 came now, sir.
Minus 6. Capital
to
A23
find
is a
the
cofactor.
Okay. For cofactor, we need to do like this formula.
Yeah. First, you have to find the minor and you have to multiply with its position sign of the element.
Yeah. Okay, sir. Thank you, sir.
Hello.
Hello.
You can ask your doubt.
Sir, can you display the first and second problem of determinants?
First and second problems. It is the first problem. Then determinant.
Okay, sir. Second problem. Thank you, sir. There was a power cut, so I wasn't there.
Don't worry. You will be given this PDF file. Don't worry.
Thank you, sir.
Yes, sir.
Hello. Tell me.
Sir, good evening, sir. Sir, can you explain the note 6, sir, last note point?
Last note point. This one.
Yes, sir.
Suppose if you take A 3 by 3, 3 by 3 means it is odd order matrix. And suppose this is a skew symmetric matrix. Third order skew symmetric matrix. If you find the determinant is 0 only.
Yes, sir.
And if you go back to the previous page, in the previous page already we have written the third order skew symmetric matrix. Third order is the odd order. If you find the determinant of this, directly determinant is always 0 only.
Okay, sir.
Okay.
Okay. Thank you, sir.
Hello. Hello. Okay, I'm closing this session.